So I'm hoping that this section will be a little bit of a review because we're going to be taking a look at how to read electron configurations and how it works with the periodic table. So to review, there are 4 possible orbitals, and we know them as S, P, D, and F. And for each of these orbitals, they have a certain amount of orientations. So we know that the S orbital has 1 possible orientation. The P orbital has those 3 dumbbell possible orientations. The D orbital has 5 possible orientations, and the F has 7 possible orientations. And so each orbital can hold a maximum of 2 electrons. So remember when we drew out our orbitals, it was those circles, and we put the up arrow for 1 electron and a down arrow for a second electron. And so each of those orbitals can only hold 2 electrons. And so the maximum number of electrons in each of these sublevels or orbitals would be 2 for the S. So this is maximum electrons. The P sublevel can hold a maximum of 6 electrons. The D sublevel, since there's 5 possible orientations and they each hold 2, we can have a maximum of 10 electrons. And then finally our F sublevel with the 7 possible orientations and 2 electrons in each of those. 2 times 7 is 14 possible electrons. So hopefully this is all a little bit of review from last chapter. And so when we look at the periodic table, we can have what we call representative or main group elements. And these are the elements that are found in the S and P blocks. That's because they follow the rules. They don't fill late or they're not behind in any which way. And so the representative or main group elements are in those S and P blocks. And so we're going to take a look at the S and P blocks in a little more detail. So elements in group 1 are referred to as the alkali metals. These metals have 1 valence electron, and they're very reactive because they only have that 1 valence electron. They're also very soft, so soft that they can be cut with like a butter knife. They have to be stored under oil or submerged in oil because otherwise they would react with the water in the atmosphere. When these metals react with water, they produce a hydrogen gas. They also easily react with nonmetals. And these elements are so reactive that they cannot be found pure in nature. They have to be combined with something. It could be combined with itself. It could be combined with another element. However, they have to be combined. Otherwise, they would be reacting constantly. In our group 2, we have the alkali earth metals. These elements have 2 valence electrons. They're slightly less reactive than that group 1, but they're still too reactive to be found pure in nature. And they're also a little bit harder than the elements in group 1. So here we have beryllium, magnesium, calcium, strontium, and barium as our 5 elements in the alkali earth metal family. So up until this point, we've kind of talked about hydrogen and helium. These 2 elements are the rule breakers to the patterns of the periodic table. So the rule breakers in that hydrogen is a gas, but it is grouped with metals. And then helium has 2 valence electrons and should be grouped in group 2. However, it's found in group 8. And this is because it has a complete valence shell of electrons. So these are the two rule breakers. But when we look at their electron configurations, their location on the periodic table makes sense. So the electron configuration for hydrogen is 1s1. And so this tells us that it makes sense for it to be placed with the alkali metals, because all the alkali metals, their electron configuration ends with some principal energy level and an S1. It does not share similar characteristics with the rest of the group other than the similarity with the electron configuration. So when we look at the electron configuration for helium, again, we can see that it would make sense for it to be placed with the alkali earth metals because of the 2s. However, it isn't placed with the alkali earth metals because it has a complete valence level of electrons. And that's a characteristic of the noble gases, or group 18. So that brings us to our noble gases. These are the elements of group 18, and they are very unreactive. That means that they are not going to react chemically, and this is because they have a full S and P block. They're completely full. There's no missing electrons. The halogens are the group 17, and they have 7 valence electrons. And these are very reactive because they're 1 electron short of that full S and P block. So the halogens want to gain that extra electron. In the halogens, we have chlorine and fluorine, and they're gases. Bromine is a dark orange liquid at room temperature. Iodine is a purple-gray solid. And then we have At. This particular element has a lot of unknowns. So not much is known about it because it's very rare. So it's hard to do research on it. So that kind of is a quick run through of our representative elements. But what about those elements in between, or those transition elements in groups 3 through 12? This is your D sublevel. And remember, it's in a lower principal energy level than the S level before it. It has similar properties as groups 1 and 2, but they're much less reactive. And you will find these elements as pure elements in nature. Then we have our F block. Remember, both of these are in the F block. The lanthanides are the 14 elements from cerium to lithium, and they have a partially filled F sublevel, that 4F sublevel. These are metals, and they will react similarly to group 2 elements. The actinides are the 14 elements from thorium to lawrencium, and again, they have that partially filled 5F sublevel. These elements in the actinides are radioactive. Only the first 4 have been found naturally. That means the final 10 have been made in the lab, or scientists have created them. The inner transition elements is what we refer to as the lanthanides and the actinides together, or that entire F block is referred to as the inner transition elements. So given an electron configuration, you should be able to give me some information about that particular element without looking at a periodic table. So for this particular one, let's maybe just make a quick little table. So we need the period, the group, the block, and the valence electrons. And so we have the first one. Again, we're going to start seeing these in that noble gas configuration. And so this element, we need to figure out which period it is in. So you look at the last item or last piece of the electron configuration, and you can see that it is in the 5th period. And so since it's in that P3 group, it's P3, that would be in the 3rd P, which happens to be group 15. Remember, our groups can be 1 through 18, and our periods can be 1 through 7. Our block refers to the sublevel, so that would be P. And then the number of valence electrons, we look at our highest principal energy level, and we have to have 5 twice. So we have to add the number of electrons together to get 5 valence electrons. This element happens to be antimony, which falls into the metalloid category on the periodic table. All right, our next example shows us looking at the last one. It is in the 7th period because it has that 7th principal energy level. It is in the, this one happens to actually be a little tricky because of this F block here. And so they don't fit perfectly into that 1 through 18. And so because it gets pulled out, we can leave that as blank. And so it is in the F block. And the reason it's in the F block and not the S block is because remember that this 7S fills before the 5F. And so we're going to be in the F block. And this gives us a americium. And this is a metal because it's in the F block. And the number of valence electrons, again, you look for your highest principal energy level. Here is 7, and the number of electrons associated with that 7 happens to be 2. So anytime you have an element in the F block for the group, you can simply mark it as an X. We're not going to worry about that. Our example C, we only have the one piece after the noble gas configuration, so that 4 tells us it's in the 4th period. And then when we count the S block, it's in that 2nd column, so that means it's in group 2. So remember, groups are also the columns. And the S indicates the S block, and again this 2 here tells us that in that 4th energy level we have 2 valence electrons, and since 4 is the highest, that would indicate our number of valence electrons. This happens to be calcium, and again that falls in the metals. Our last example here is osmium. And osmium is a metal. And so looking at our electron configuration, we look for the period, which is the highest one here, which would be the 6th. However, when we look at the rest of these, we can see that we are in the F, and now we have filled into the D block. So this F block is completely full because of 14. F can hold 14 electrons. The D block is only partially filled. Actually, that one is also completely filled. No, it's partially. Because the D block has 6 electrons, but it maxes at 10. And so the group that we would be in the 8th group, because we have the 6S, the 2 groups over for the S, plus the 6 groups or 6 columns that you'd have to count across to get to that D6. Our block is the D block, and the number of valence electrons, we look for our highest energy level, which is 6, and we look at how many electrons are in there, which would be 2. So there are 2 valence electrons for that particular element. So worst case scenario, you have to look at a periodic table to help you out, but you should start to try and wean yourself off of the periodic table and try to be able to answer these questions with just looking at the electron configuration.